All right. Hi, everybody. Welcome to the Chapter 6 review of the electronic structure of the atom. This is for our Gen Chem 1 class, and this is the fall of 2024 that this video is being filmed. So just to kind of start us off here, what I've done is I've taken the learning objectives from each section of Chapter 6, and I've put them up. And what we're going to do is we're going to use these learning objectives as a task list, aka like a skills list. We're looking for these skills to be ones that you've acquired in the course of this particular chapter. So in section 1, we start with identifying the different types of electromagnetic radiation and arranging them in order of their relative wavelength frequency. You can see that we're up here in 6.1. In order to help us with some of these, I've added some of our equations already. So these equations we're going to talk about for section 2, or the second learning objective. But for section 1, I've also added a diagram, and that's our EM spectrum. You would be given this on your quiz. One of the things I'm going to aim to do in the course of this video, I already went through and changed wrote a bunch of things out. What I'm going to try to do is anything that's going to be given on your quiz so that you know it, I'm going to try to identify that in like a different color than what I've already recorded a lot in, so that you know what will be given. Okay, so this electromagnetic spectrum is going to be given to you. Remember that you had some questions over this on your homework set, and that we also looked at on in different aspects. But one of the things you were asked to do is, given a wavelength, determine if it would be detectable in the X-ray range, or if it would be detectable by the human eye. Always using the wavelengths to do that type of a question. Generally not using frequencies to determine if it would be detected, just so we are aware. So using the electromagnetic spectrum, kind of describing that the things that are not harmful are going to be down at the end, and the things that are harmful are going to be at the other end. Remember, we said the smaller the wavelength, the more likely it would be able to move through things. The larger the wavelength, the less likely it is able to move through things like thinking human tissue and atomic structures and just general materials all around. So the more damaging types are going to be like the gammas and the UV and the X-rays, and the less damaging are going to be longer wavelength things like radio waves. Now that's part 1 of section 1. Section 2, or part 2, says to be able to calculate the frequency of radiation from wavelength and vice versa. So if you're given either the wavelength or the frequency of some radiation, you should be able to calculate the other, given the fact that the speed of light is constant. So all of that electromagnetic radiation moves at the exact same speed. That speed is a constant, again, a number you would be given, okay? 3 times 10 to the 8th meters per second. You'd also be given the equation, not the description of what's in the equation. So make sure that you understand wavelength should always be in meter, frequency should always be in inverse seconds, aka hertz. The speed of light is always going to be the constant 3 times 10 to the 8th. Moving on to section 2, one of the first things you're asked to do is to be able to explain how radiation and the photoelectric effect provide evidence that our EM radiation is quantized. We talked about this kind of referencing this staircase idea. We said that if the energy was uniform and continuous, that we would not see what we see in things like the Bohr model. Okay, or in like the line structure that we're going to see later on in this section. In fact, what we see are that energy levels are discrete energy levels in that they move up in a specific amount. And this diagram is kind of a misnomer. It shows that all of the steps are equal. Not all steps are going to be equal. And as you see, as you saw when you were doing some of your math, hopefully you finish your problem set, but in that problem set, one of the questions you were asked to do was to determine the change in energy for a photon that moves from like an n of 9 to an n of 4, or from an n of 4 to an n of 9. You were asked to determine what the change in energy would be. That step is going to be a lot different than a step that might go from, say, n of 4 to n of 5. Okay, so the quantized energy part of that we talked about in class had a lot to do with the fact that light really does behave this way, and we know it behaves this way because we're able to understand this equation we're given, that the energy of a particle is related to its frequency in hertz, Planck's constant, which is given as this, again, constant number. Constants are always given on quizzes and tests, as are formulas. And the equation would also be given. The energy of a photon is equal to Planck's constant times the frequency of light. Could we also then use these two equations, like you did on a few of your problems, to determine maybe the frequency given a wavelength and then an energy given that frequency that we calculate? Absolutely. So be able to use these two pretty interchangeably on your quiz. All right, in section 3, we're talking about the Bohr model for the first time. Really, we've kind of set ourselves up before this with the Bohr model, saying that, a ground state energy level is one where we start with a low energy, and then if we want to move to a higher energy, there's going to be required an amount of energy input. So all of these transitions that you're seeing with all of these different arrows in this diagram, they're all representing essentially some type of an energy transition. That energy transition then can be translated into wavelengths of light. And in class, we talked about how not all energy transitions are going to be defined as having some energy that is located in the visible range, but a lot of them do at least have a few transitions in the visible range. So when we look at something like hydrogen, we see that there are electrons that can perform 4 different transitions. In fact, in this diagram, I think what they're trying to show you is that these are all hydrogen transition, these first 5 or so lines. And those transitions can then they correspond to a specific amount of energy using that equation, E equals hv. All right, so determining these transitions is part of that line spectrum. All of those transitions are related back to those energy transitions, and that's using the Bohr model to calculate what they are. This formula that we discussed in class and that you used on your homework set would also be given to you, but essentially you're trying to figure out how much energy there is in a specific energy transition. So let's say you move from an n equals 1 to an n equals 2, your final would be your n equals 2, your initial would be your n equals 1, and you do 1 over 4 squared, 1 over 4 minus 1 over 1 times this constant value. From there, we move into wave properties of matter and how they actually affect the Bohr model, since the Bohr model really just depends on electrons and or photons acting as particles and not as waves. This brings us into this discussion we had in class about the dual nature of matter and how we have to treat our electrons as if we can't know both position and momentum at the same time. Essentially what that means is by the time we locate something moving so fast, it's already moved on. So the closer we get to measuring one, the further we get from measuring the other. I want to point out that these things will not be given to you on your equation sheet, but that it is important that you understand that this Heisenberg uncertainty principle it comes from a place that identifies that because our matter is behaving as both a particle and a wave, that there are limitations, and those limitations are referred to in the uncertainty principle that was proposed by Werner Heisenberg in the 1940s, 1950s. So from there, understanding that we cannot know both momentum and position, we move on to those probability diagrams. Before we get there, though, and we're going to talk a little bit more about quantum numbers because quantum numbers are going to come into play here, but essentially the quantum numbers aim to describe why the uncertainty principle is what it is. They also use the idea that our electrons have to have specific characteristics. So over here on the left, I've gone through and I have outlined what each of the different quantum numbers are, just to remind you. The first thing I need to remind you of is the fact that quantum numbers are characteristics. The first quantum number was given by a letter n. Remember, n represents the size of orbitals and gives us the amount of energy that the orbital might have. So an n equal 1 is going to have lower energy than maybe an n equal 3 or an n equal 4, and so on and so forth. And it also indicates the distance from the nucleus the electrons can be found in, the rule for n, and each one of these has a rule and some examples moving forward. But the rule is that n has to be a number from 1 to infinity, and it must be a whole number. N cannot be 0 is a big takeaway there, because every other quantum number has a 0 except for ms. So rule number 2 is on, quantum number 2 is angular momentum, L, which is representing the shape of an orbital. And what we call an orbital is defined by those probability radial functions in section 6. So I wrote probability of finding an electron in this area is very high. That's where we're going to come and we're going to look at 6.1. I apologize. My dogs are just making sounds in the background. I'm trying to get through this. The rule for each value, the rule for L is that for each value of n, L must equal 0 up to n minus 1. All of those values. It must equal all of those values up to n minus 1. Now, could we identify something like 4F as a specific subshell that we want to describe? Yes. What that indicates is that we are in principle number 4, and the shape of the orbital that we're talking about is an F orbital. So just kind of understand that when we use those values or those designations, what we're trying to do is we're trying to get closer and closer to describing specific electrons and further from describing all electrons with an N of 5 or all electrons with an L of 2, because there are going to be a lot of them for each of those categories. So the rule for L just is that it ranges from 0 to n minus 1. The example here says that when n equals 3, L must equal 0, 1, and 2. And then in the magnetic quantum number m sub L, we take it a step further and we say that the L values, for each L value, that there must be a specific number of m sub L values. So the magnetic quantum number aims to describe how many orientations there are in three-dimensional space for each orbital shape. Remember that there was also a chart that we looked at when you had L and you had shape, where L is 0, the shape of the orbital is an S orbital. When L is 1, it's a P. When L is 2, it's a D. When L is 3, it's an F, and there isn't anything beyond F. But remember that that chart kind of also describes what the shapes are. For some reason, we decided that numbers were not adequate to describe shapes, so we started using letters to describe shapes. I don't really understand. I think they actually technically represent specific descriptions of the shapes. So like S is sphere because an S orbital is a sphere. I don't know what P stands for. I'm sure it's some Latin term for the shape that the p orbital makes. Same with D, same with F. But the number of orientations in three-dimensional space for each of the orbital shapes is going to be your next quantum number. For each L value, m sub L has to equal all values from negative L to 0 up to positive L. And when we say all values, we always mean whole numbers in these different types of quantum numbers. So here we have an example that for an n of 3, we know L is 2, 1, and 0, and we know m sub L has to equal then negative L up to positive L. What I did was I also counted how many orbitals each of those values represents. So for instance, when L is 2, m sub L equals negative 2 up to positive 2, including 0 representing 5 orbitals or 5 orientations in space. So this one is like the d orbitals because, of course, 2, L is 2 is a d orbital. What that means is that there are 5 different d orbitals. We know this because we've done electron configurations before, but there are 5 d orbitals. You can fit 2 electrons in each. Now, you'll notice that the spin quantum number is not discussed here. That's actually not discussed until a farther section. So that's all of section 5, really. The first one says to talk about Schrodinger's model versus Bohr's model. Schrodinger's model includes the quantum numbers and how electrons have to be found in specific probability maps, whereas Bohr's model says that everything is at discrete energy levels and they orbit in specific spherical orbits around the nucleus. So remember, Bohr's model of the atom is only good for one atom, and it's hydrogen. Schrodinger's model kind of goes a little bit further and says we're going to use more characteristics of the waves in order to describe them. And then these other two are about quantum numbers and making sure we understand how to use quantum numbers. This last one kind of talks about arranging the orbitals in order of increasing energy. So this is where we get a orbital diagram where we start with 1s, then we go up to 2s, then we go up to 2p. Sorry, this is really, really icky. I'm not trying to make it pretty. Then we go up to 3p and so on and so forth. So that's kind of what it means when it says arrange these in order of increasing energy. In the next section, you're asked to interpret a radio probability function of an atomic orbital. That sounds like a very scary term, but essentially that was our very brief discussion on how, if we're looking at different orbitals in different energy levels, so for instance, this is a 1s, this is a 2s, and this is a 3s. When we're looking at these, what we see is that in each, as we increase our number, there is going to be what we call a node. Remember, we said a node is the place where you will not find an electron. So node equals no electron, if you will. It's like a no electron zone. Absolutely nothing is supposed to be found there as far as electrons are concerned. So the radio probability function is essentially just there are nodes between different energy levels. And if we're looking at 1s, 2s, 3s, or if we're looking at like 2p, 3p, 4p, there would be a node in between each one, is essentially what we're predicting using these radio probability functions. Okay? I don't want you to worry too heavily about that, but I do think it's important that you understand what a node is. You definitely need to know what a node is. I will ask you that. I'm just going to tell you. Because it's a very important concept. The difference between a 2s and a 3s orbital is the presence of this node, in that it separates those two different types of orbitals and or probability densities. It also would help us identify an electron as either a 2s or a 3s electron as far as the math is concerned. Okay? Compare and contrast the three-dimensional shapes of s, p, and d orbitals. I feel like we look at s, p, and d orbitals in class. You know that these are s orbitals. P orbitals have 3 orientations. We saw them in lecture. D orbitals have 5 orientations. Be able to recognize a d orbital from a p orbital. That's my advice. Be able to identify an s orbital versus a p orbital versus a d orbital. If I give you a picture of something and I say, what type of orbital is this? You should be able to tell me that's a d orbital, that's a p orbital, etc., etc. Okay. The next section talks about energy levels of atomic orbitals in a many electron atom versus a hydrogen atom. So essentially this one is saying, be able to tell me why the Bohr model is not good. Right? We said the Bohr model is really great if all you're dealing with is one electron in an atom. The more electrons you add, the more complicated the transitions are going to be, and they're going to overlap, and there's going to be a lot of places where we're looking to find electrons. So essentially we're saying Bohr is very inadequate compared to maybe this Schrodinger probability or this new atomic orbital theory that we're talking about. And then in this section, we also introduced spin quantum numbers, aka the m sub s number. We said one of the questions I'm asking here is, why does the spin quantum number matter? And how was it discovered? And the answer is magnets. Okay, we put some electrons in a magnet. We put 2 or 3 electrons. We put maybe probably 1,000 electrons in a magnet, and we watched which direction they spun. And what we noticed was they spun either positive or negative. Apologies. Okay. And what that interprets for us is that 2 electrons can be found in the same orbital. Each m sub L value now has an m sub S of positive 1/2 and negative 1/2 is the official rule for this quantum number. But the answer to the why is because when we shot electrons through a magnet, we saw that they spun in one of 2 directions. And we defined those 2 directions as a positive spin or a negative spin. We also said if they can have those 2 spins, that they can pair with each other, and that would create the lowest possible energy in that specific orbital. The reason we say 2 electrons and that they must have opposite spins is because we noticed that that is a lower energy option than having electrons move up. In other words, we have to fill all of the... Ooh, I'm doing that wrong. Please don't learn from me there. Okay? Remember, we have to fill each one individually, but what this particular discovery of the spin quantum number is says that according to the Pauli exclusion principle, that electrons would prefer to spin in the same energy level. So let's say this is 3s. Instead of having our electron move from this energy level up, it is a lower energy thing to do to place the electrons in spin-paired orbitals, and then after that, we move up to the next energy level. Okay? So this is described by the Pauli exclusion principle, which states that each electron must have 4 unique quantum numbers. So positive and negative spin are the 4th quantum number, and each electron can have an N value, an L value, has a unique N, L, M sub L, and M sub S. No 2 electrons can have the same 4 quantum numbers, is what the Pauli exclusion principle says. Okay? In the next section, we say you should be able to determine the expected ground state electron configuration of any atom and use various representations to express it. Okay, so what does this one actually mean? Okay, this means use the periodic table to write full and condensed electron configurations. And remember the order of filling. So, we start with 1s. We put 2 electrons in it. Then we go to 2s. Then we go to 2p. P orbitals can have up to 6. Then we go to 3s. Then we go to 3p, up to 6. Then we go to 4s. Then we have 3d. D orbitals can have up to 10. 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, today, nope, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. So that's the full electron configuration all the way up to the end of the periodic table. So this is element 118. Okay, and I'm drawing in the barriers between the noble gases. So at the end of these, remember that there's a noble gas that you can put. I'm going to ask you to reference a periodic table. I don't have one in front of me at this moment. Okay, so here's another one. After every P is the end of the row, aka a noble gas. And remember that when you write the condensed configurations, you start at the noble gas, then you move down to the next row. Okay, so full electron configurations don't have the noble gas in them, and condensed ones do. Okay, Hund's rule is in the next part of section 6.8. It says use Hund's rule and an orbital diagram to determine the number of unpaired electrons for any atom or ion. So if I give you a diagram like this, okay, if I give you this diagram and I say put silicon in this diagram, then what you're going to do is you're going to figure out where silicon is. You're going to fill each orbital from lowest energy to highest energy. Remember, you're going to do one electron. So for p orbitals and d orbitals and f orbitals, you do one electron first, then you go back and pair, then you move up to the next level, one electron, then pair, then you move up to the next level, one electron, one electron, one electron, then pair. Okay? So when we're doing that, just remember that what you can do is you can end up with unpaired or unoccupied orbitals. So something like silicon is only going to have 2 electrons up here, and then it's going to have a whole orbital not filled and 2 unpaired electrons. So a question I could ask you is, how many unpaired electrons does an atom of silicon have? And you would say 2, right? Because that's the only set of orbitals that's going to be missing electrons. Okay, so that's what that means by 6.82. You always fill lowest energy first, pair before elevating to next level. Okay. Next is, and very last part of this chapter was, how is the periodic table organized in relation to the electron configurations? The answer is, you guys know that there is an S, P, D, and F block. So if we look at a rough outline of the periodic table, you remember that these are the F, these are the P, these are the D, and these are the S. That's what it means by explaining how the organization of the periodic table arises from electron configurations, and be able to identify and name various blocks of elements. So for instance, the S orbitals are the alkali and the alkaline earth. The D orbitals are the transition metals. The F orbitals are the actinides and lanthanides. And the P orbitals tend to have the halogens. And they've got, the nonmetals, and there's a couple of other, interesting characteristics for p orbitals, but there aren't like general blocks aside from the halogens and the noble gases present in the p orbitals. All right, so that covers all of chapter 6. All right, pretty interesting. Got through that in less than half an hour. Very, very proud. One of the things I want to do is I want to recommend some exam prep resources for you. You've got the end of chapter. There is a section called exam prep. There are 26 questions, and as you answer them, it gives you a check your answer thing, where it also tells you why the answer is what it is. It won't necessarily tell you if you got it right or wrong. You can answer it before you look at the answer. I highly recommend you try to answer them before you look at your answers, that there also are some with videos. You can also click this little symbol on there to look for videos related to the specific questions or this specific prep that you're doing. At the end of each section, there are also these self-assessment exercises, or SAE questions, that you can answer, and those also give you your answers, so you can answer them and you can see if you got it right or wrong. Okay? All right, happy studying. I will see you I will see some of you on Thursday. Have a great evening.